Hello, I'm John DeGonia. Welcome to my Lab 3 presentation. In this lab, we're looking at estimating forces and the mass of a black hole from the movement of a star around said black hole. So we're going to be taking observational data, just data points where the star is. We're going to extrapolate knowledge about the system, mainly the magnitude of the change in momentum, and then we're going to use Newton's second law to turn that momentum into FNet. So first we're going to be iteratively calculating FNet from position data, and then we're going to be splitting the FNet into its parallel and perpendicular components. Then we're going to use all that information and the force of gravity equation to get the mass of our black hole. So what do we have to start out with? Of course, we've got the position data of the star as it orbits around. We've got the location of the black hole. It is conveniently in the origin, the very center of our model. Star mass, time step that's just equal to 1 day, and the gravity constant. So the most complicated part, in my opinion, is the iterative process of finding FNet. In the bold text, I've got what's basically going on, and then the specific code under that if you'd like to read it. So we need to go all the way from position data, which is just position points, to FNet. How are we going to do that? We're going to take the first 2 position points, find a velocity, then the second and third position points, and find a final velocity. With initial and final velocity, we get a change in velocity. And then we take the change in velocity, multiply it times mass. Of course, mass times velocity is momentum. And then now that we've got momentum, because you can see on the right, in every situation relevant to this lab, change in momentum is going to be equal to force. So we've got change in momentum, and so we're going to take that as our net force, and then we're going to repeat this process over and over again to get a constantly updating net force. So now that we've got our net force, we need to do a little bit more. We need to split that net force into perpendicular and parallel elements. How are we going to do that? Well, we're going to take p hat to be the direction of our motion, so we can get our parallel force. So take p hat as the direction of our motion, and that way our force parallel will be the force in the same direction as p hat. And then from the remaining force we can get our perpendicular. How are we going to calculate the mass of the black hole? Well, we're going to use our force of gravity equation. Fnet of gravity is going to be equal to all this. Rearrange it to get the mass of the black hole. But we don't have a radius because, as you saw earlier, our radius is changing over time. What are we going to use as radius? Well, I'll tell you. We are going to use the radius of the Kissing circle. And it's calculated as seen. Of course, we're going to be using magnitudes because the mass of a black hole, our end result, it's not a vector quantity. It is a stagnant. It's just mass. So we don't have to worry about directions. We just need magnitudes. And then we're going to plug all that data to get the mass of the black hole at the very end of our equation. So let's look at the resulting data here. We've got FNet, FNet parallel, and FNet perpendicular at the very end of our simulation, the last point. And then we've got the mass of our black hole. It is, of course, supermassive. Let's look at the simulation here on the right. So our orange arrow shows FNet. That's why it is, of course, always pointing directly at the black hole, because there's no other forces acting other than the force of gravity. The blue arrow, FNet perpendicular, and the purple arrow, FNet parallel. You can see here as the star gets closer to the black hole, you can't see it, but it's about right here where my cursor is, the forces are increasing. That's because, as you saw in the force of gravity equation, the closer you get, the less the radius, the stronger that force is going to be. And you can see also, as we're getting closer, the force perpendicular is increasing, and at a certain point it will match the FNet as we are reaching the point where we stop going closer and start going farther away from the black hole. So let's talk about a few things. Force components versus change in momentum components. Now mathematically we know these things are going to be the same, but the crux of this lab is we know that the momentum change is observable, but the forces are not. So we've got our momentum change, and mathematically they're the same, so that we can take something observable and turn it into forces, which we cannot easily observe. Thus being the main difference between the two. And then our what if our black hole was replaced by a different one, an imposter black hole, in the same place, and we observed identical motion, we would assume an identical mass of the new black hole. Why is that? Our FNet consists only of the gravitational force on the star by the black hole, which depends only on distance and mass. So same place, same mass, it'll have to be the exact same black hole if our orbit is the same. Thank you for watching and have a nice day.